Unusual LED lamps and cookies, maple cookies from Canada, sent by Kim, who also sent us some MREs to try out. So we'll be doing them later on. But the star of this particular video was suggested by a friend called Peter, who said, I know you've done some of these LED flicker flame lamps, but this one is very, very different. I'd recommend you get one and see what it's like. And this eBay seller had run out of them, but by looking at the image, there was one that was particularly distinct of the casing. And it's a translucent case that comes down, and then it sort of overlaps onto the white base here. So it's a typical looking lamp, other than that sort of design feature. And I'm going to have to say, you just don't know what you're getting at the moment, because these lamps are evolving so quickly. This, I think, is one of the latest evolutions. It's got the same feature that you've got the 3 effects, and it always defaults. If you turn this off and leave it off for a length of time, then when you turn it on, it'll always default to the flame effect, which is really the main effect in this. It's only drawing about 1.6 watts of power. Terrible power factor, suggesting the... Well, I think it's... Yeah, it is a switchboard power supply. If you turn it off and on again, let's do it at the hoppy. It goes into static mode, turn it off and on again. It does the completely useless ramping up and down mode. And then turn it off and on again, it goes back to the flame effect. Now, what makes this lamp particularly special, I'll unplug it before I do this, is, I'll just chuck that box down there. Let's unscrew this. Shove the hoppy to the side. This comes apart Tupperware style. And whereas the other ones have had a circuit board, a power supply, this one has a power supply in the base, and then a circuit board with the round circuit board, the flex one above it. This one is just one solid piece of flexible circuit board that is rolled round in itself, and all the circuitry is down the left-hand side. You've got a microcontroller, you've got 16 transistors, a voltage regulator, one resistor for all the LEDs, which is a bit odd, but it doesn't get too hot, and then all the LEDs themselves. And it's clearly designed to scroll round onto itself and then solder onto these points here with the circuitry just sort of tucked inside. But this one wasn't. I don't think it would fit in if you did that. So what they've done is they've just sort of loosened it up, they've shoved it in, and then they've let it expand out. It's worth mentioning that for extra diffusion in here, there's also a plastic tube in here, a sort of liner, that is quite well perfectly spaced. I mean, it looks like it's been moulded in, but I think it's a separate one that's been glued in afterwards. But it provides a double layer of diffusion with a little sort of air gap between them. It's very precise. The circuitry is based on a little power supply in the bottom here. Let's get this out. Is this going to come out? It might not come out. It is jammed in, it's glued in, I think. All right, okay. But what I can tell you about that power supply is it's a 12-volt power supply, and it is unfortunately referenced to the mains. Let me prove that it's referenced to the mains. If I turn my continuity tester on, in the true style of the fact it's going through a bridge rectifier, if I go into the positive and negative connections here and I just try all combinations, so let's go from the positive onto the shell here, that is immediately showing you've got a response there. It's not a decisive response, but what about to the bottom there? Nope. So let's try the negative connection to the shell, and that is a diode. And that suggests there is a direct connection through this. So although it's a 12-volt supply, it is not isolated. So resist the temptation to go, ooh, and pull it all out while it's plugged in. Go look at that, and then grab something that's earthed, and find yourself getting a real flame effect through your fingers. So the circuitry is very interesting. I'm going to zoom down on this and we shall explore it in greater detail. It's a very neat circuit board. It has all the LEDs and they're wired as multiples of 3, even though they're used as pairs in each section, which is echoed along there. You've got the, hold on, if I mask off there, that's one section, and then that's repeated again, and then it's repeated again. And I'll discuss later how the LEDs are wired, but they are wired in multiples of 3 to match the 12 volts. There is just this one resistor doing that, the job of limiting the current to them all, and you'd think that would get quite hot. So I got the thermal imaging camera out and I looked at it. Ignore the fact that the outline that it superimposes over the thermal image is slightly out of a line here, because when you're up very close, the two cameras are at different positions and it shows that it's being different. So although it looks like a heat spot is in the middle of all the LEDs, it's actually just below the LEDs. That's the resistor. It was a temperature of about 44.2. Ambient temperature was about 7.3. It's less than 40 degrees above ambient, and that was on static when all the LEDs are lit continuously, because that's when it draws the most current. The other little dot of warmth was that bit there, which it's actually underneath the chip as opposed to above it, which was the voltage regulator. I shall show you that right now. So here is the circuitry. There's a current limiting resistor, the LEDs, the microcontroller. It's got the little capacitor there across the supply, a 78L05 voltage regulator, and then a diode feeding a capacitor, and that then powers the chip. The chip drives these transistors via resistors, which then switch the LEDs down to the negative rail. And that's all there is to it, really. It's quite a complex and densely tracked circuit board. It's double-sided and it's absolutely covered in tracks. I'm going to zoom back out again, and I'm going to bring in the data that I have gleaned off this. So I've already been doing some exploratory work in this. I'm looking for my pen. I have lost my pen. There's a pen. The LEDs are in pairs like this. It's a really common style for the animation, but because they're wired in multiples of 3, and there's 3 sections of this, these LEDs are sort of wired as a pair, plus they share one LED from the next set, and then the far end one, it also has the pairs, but they share the other LEDs. So the middle one has quite a lot of more tracks and quite a high density of tracks, because it's sharing its LEDs amongst the others. The exception to that is the tip of the flame, which is, as usual, it's 3 LEDs, and they're just treated as a separate clump of 3 LEDs each time. The CPU is not marked. It's an 18-pin chip. Pin 5 is 0 volt, pin 14 is technically 5 volts power. It's the positive volt rail, but in reality, because the circuitry here, it's going to actually get about 4.5 volts. And the circuitry is very simple. You've got your 12 volt rail coming in, one common resistor for all the LEDs. So technically speaking, that is multiplied by about 16 sets, with one of them, the peak one, having another set of 3 LEDs in parallel with that, just to make up that larger number of LEDs, dimmer LEDs at the peak. The supply for the CPU is derived from the 12 volts. There's a capacitor, locally a decoupling capacitor, a little 78L05, let's write 78L05, really common voltage regulator. And then it feeds the chip, but via a diode, and there's another little decoupling capacitor, which is also probably doing that timing thing, that it's just to introduce a very slight time delay for that on-off changing the effect thing, which is kind of pointless. There's a 1.6K resistor to each of all the 16 transistors, and this is where it all goes a bit weird. You see, I was just probing around and said, oh, that'll be an NPN transistor because it's switching to the negative rail. It didn't really measure out as an NPN transistor. It measured out as a PNP transistor. I checked it up. It's a 2TY, which is a PNP transistor, which normally switches to the positive rail, but in reality they're switching to the negative rail, which is odd. I'm not sure why they did that. A couple of things come to mind. Someone may have screwed up and got the wrong ones, but it worked. Or they might actually be deliberately allowing for the fact that that introduces a slight current limit, which is just very, it's an odd way of doing things that might balance the LEDs a bit. I really don't know. I really haven't a clue why they've used a PNP transistor instead of NPN. It's very strange, particularly when the circuitry is perfect right up to that point. Then it's just that little mystery. The current, at 12 volts, it draws 100 milliamps in the flame mode. At static mode, it's 180 milliamps, and the arrangement of it in the flat panel. Hold on, you know what? Let's cut this off. Let's connect it to the 12 volts here. I'll connect it to the bench power supply. So let's lock these off, and I want to get that power supply out here as well. So I'll also break this out, and we'll take a look and see why it was passing it was showing continuity to the mains side. It seems quite odd. Normally with that type of circuit I would kind of expect an isolated supply. It doesn't really... I'm not sure why. A regulated buck converter? It's odd. If it is a buck, I would have thought it would be isolated. So I'm just going to take this away and bring in the power supply. And we'll turn the voltage down and we'll see what voltage it kicks in at. One of the nicest things about this is that if you've got an application where you want a larger area of flame, you can mount it flat. You could almost mount it in a picture frame. Let's get the polarity right so I don't immediately nuke the thing. And there's no visual output yet. The voltage is too low. Let's turn it up until the flame effect starts. Okay, it's starting about... It starts appearing at about 8 volts. And as you at that, you can see the visual effect. I could actually turn the light off here. And I could take the exposure up here. So at that, it's literally at 8 volts. It's giving a modest visual effect, but it's only drawing 5 milliamps. That's ridiculous. As I turn it up to 9 volts, it's drawing 20 milliamps, and that is bright. 9 volts at 20 milliamps, that is ridiculous for how bright and visual it looks. You know, this would be more than enough in a home environment, just if you're looking at something not to be offensive. But as you turn the voltage up more, let's go up to 10 volts, and this is where the camera's going to kick in and tame it down a bit. At 10 volts, the current is 50 milliamps. 11 volts, 80 milliamps, and going up to the full 12 volts, it's about 100 milliamps. And it's quite actually offensively bright now because it really would need diffused at that. So I quite like the fact that way down at 9 volts, you're getting a good visual effect. At 20 milliamps, it makes me wonder how long this would run off a PP3 battery. I mean, gradually the voltage would go down to tail off quite a bit, but it would do quite well. That's interesting. So I'm just about to turn the light back on, so suddenly it's going to be Swamporama. You ready for this? Whoa. And we'll lock the exposure off again so it doesn't waver up and down. So I think this is worth buying just for the panel as a sort of visual effect. It lets you either put it out flat or even just arch it round a sort of 180 degrees, which would still give quite a large coverage and give that larger flame effect. Right, okay, the next thing, we want to get into this. This, I'm guessing, is glued in. Must be glued in because it's not coming out easily. Let's use unreasonable force. I'm not particularly fond of a 12 volt power supply that masquerades as low voltage, but oh, this might not be coming out. Is that glued in with solid hard resin? I think it may actually be glued in with solid hard resin. It's never stopped me before though. Let's not close the pliers on my hands. Oh, that'll be it then. Oh yeah, it's really, it's that hard white resin they've used. So let's slit this open and see why it was referenced directly to the mains. I mean, guessing it might just be a buck regulator. So the transformer does have 1, 2, 3, 4 pins. It almost looks like an isolated supply. What is the number of the chip? H&M Semi HM2741. You're going to be able to see that? Possibly not. I'm not sure, actually. You know, you've got the advantage of the much bigger screen than I have, so at some point this will be in focus. The transformer, I'm guessing, is just probably... It's strange that, you know, For all the extra work, it would have been so easy to make this an isolated supply, but ultimately it's inside a lamp, so they don't really have to. It's just a shame that this isn't an isolated 12 volt supply, but yeah, there's continuity right across from one side to the other, so it is really just completely referenced to the mains. So that must maybe just be using a choke, an inductor, instead of a transformer, and then just sensing the voltage at the other side, and it'll have some sort of threshold setting. Odd. Yeah, very strange. But, yeah, I definitely like this panel. This panel is very neat. I can think of lots of uses for this. I don't get that use of PNP transistors. If you get any thoughts about that, tell me in the comments below. It's quite strange, but this is a very nice panel. It's really quite smart. One final piece of the jigsaw. Why did they use a buck regulator? And the answer is that it was the simplest solution. I looked up the HM2741 on Google, and it instantly came up with the PDF file, the datasheet for it in the first hit, which was very good, and it's in English. That makes it even better. And what makes this special is that if you look at the integrated circuit on the circuit board here, you'll see that pin number 3 is not connected, and that's the feedback pin. And the reason for that is if you look at the datasheet, it says default 12 volt output with feedback floated. So basically speaking, without components connected to that, it will automatically set a 12 volt supply, which is exactly what that little circuit board needed. The circuit board itself is quite nicely laid out. It's got the very low component count. The supply comes into it, and first thing it goes through is this FR1 fusible resistor 1, which they've just used as a 0 ohm link. Now, the surface mount resistors are a little slab of ceramic material with a coating on them, a conductive coating. And in this case, for the 0 ohm link, it's just basically a highly conductive coating. It's got very low resistance. And the normal application for a 0 ohm link is just to shunt out pads that perhaps you had multiple resistors in series and decided not to use that. You can shunt them out, or it's also sometimes used to jump over tracks that pass underneath. It was just a convenient alternative to what would have been a link in a traditional circuit board. But in this case, they've used it as a fusible resistor, and I'm guessing that with enough current, the coating on that is going to just go bang, and it's probably got fairly low mass, so it probably will blow clear. So it goes through that fusible resistor and then to the bridge rectifier. The bridge rectifier converts the AC into unsmoothed DC, which then gets smoothed by this capacitor here, which is the electrolytic, which is a Chongx 10 microfarad 400 volt capacitor. The positive connection then goes to the integrated circuit. It's interesting that all 4 pins at that side are, presumably it's for heat sinking, but they're connected to the common positive there. There's a 1.2 ohm sense resistor that's used to sense a peak current in the circuit going through the inductor. And then really after that, you've got the output capacitor there hanging off the end. And then just 2 diodes, the capacitor and that sense resistor, and that is it. So it's a very, very low component count. And it kind of tallies up with one of the example schematics, the application circuits, although the notes, they're very, very small compared to the rest of the data sheet. It would be nicer if they just scaled that up a little bit. But the way this works, the inductor limits, it stops any sudden high flow of current. If you pass current through it quickly, it will try to build up a magnetic field, and in doing so, it sort of restricts it almost like a resistor, but not giving off heat. And also, unlike a resistor, you can't just rely on that continuous. It can only be done in pulses to build up the magnetic field, then let it collapse again. So what this circuit does, if the voltage in this capacitor is below the 12 volts, it'll allow pulses of current limited by this inductor to actually enter that capacitor to charge it up until it reaches 12 volts, and then it will sort of stop providing those pulses until the voltage drops again. It just basically keeps it topped up. And it can do that directly from the mains, because ultimately in this case, the circuitry that's powering this panel here is inside a plastic enclosure away from touch. So it just makes it viable to have that 12 volts reference to the mains. So it's an interesting thing. It's quite a complex circuit. There is a page 3 of the data sheet is just a block diagram, and it's stuffed with circuitry inside. It's got lots and lots of modules and protection and feedback and stuff like that. Quite an interesting thing. Notable that it says with audio noise free operation. I think that is to do, Yeah, it's not got a fixed internal clock. So I'm guessing that just spreads the switching over a sort of larger spectrum, so it is a quieter unit. It's not just going to whistle at one frequency like many other switch mode power supplies. So it's a perfectly logical choice for that application where you wanted a low component count 12 volt supply to power these LEDs. So yeah, it's a reasonable choice and quite an interesting lamp.